In this video, I'm going to cover lattice energy. So on top of the enthalpy changes that you have learned in AS Syllabus, like enthalpy change of formation, ionization energies, we are learning these three new enthalpy changes: lattice energy, enthalpy change of atomization, and electron affinity. So that later in this chapter, we are going to use them for calculation. So the first one will be lattice energy. The definition of lattice energy is put in this box. So lattice energy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. For easier understanding, let's look at this equation. I have 1 mole of sodium chloride, which is an ionic compound, is formed from its gaseous ions. So in sodium chloride, the cation is sodium ion and the anion is chloride ion. So gaseous sodium ion and gaseous chloride ion bond together and form the ionic compound sodium chloride. 1 mole of sodium chloride is formed, so the energy that is released by these two ions bonding together is the lattice energy of sodium chloride compound. Now I have 4 different ionic compounds here. I want you to practice writing equations to show the formation of the ionic lattices for these 4 different ionic compounds. Just like the example that I've shown you in the previous slide. 1 mole of sodium chloride is formed from its gaseous ion. So by looking at the formula of compound, I know that the cation is sodium ion and the anion is chloride ion. Do not forget to include the state symbols because we are writing these equations following the definition, and the states of the reactants and products will always be included in the definition, therefore they must be included in the equation. You can pause the video while you write your equation, then you can continue playing this video to look at my answers. Okay, we'll come back from writing your equations. Now you can check your equations against mine. A few points to summarize from these equations. Ionic compounds, they have high melting points and boiling points, so they are always solid under standard conditions. So state symbols for all these ionic compounds must be solid. According to the definition, ions are in gaseous forms, so they are all gases. We are coming back to this slide. Lattice energy again is the energy released when you have gaseous cations and anions bonding together to form ionic compound. Like the equations that we have written for the previous exercise, different ionic compounds will have different cations and anions. So they will have different values for lattice energies. Some are more exothermic, some are less exothermic, but they are always exothermic because formation of bonds will always release energy. So the more exothermic is the lattice energy, the stronger is the ionic bond that is formed between ions. The first example given here is sodium chloride. Lattice energy is negative 787 kJ per mole. So let me write another example, magnesium oxide. Lattice energy is negative 3,923 kJ per mole. So if we compare these two lattice energies, lattice energy of magnesium oxide is more exothermic. So this is telling us that the ionic bonding between magnesium 2 ion and oxide ions are stronger than the ionic bonding between sodium and chloride ions. So what are the factors that are affecting these lattice energies, making some of them more exothermic and some of them less exothermic? We are going to look at 2 factors here. The first one will be the size of the ions. Lattice energy will become less exothermic when the size of ions increases. When cations and anions are bonded together, positive neutrons in the nucleus of the cations are attracting the electrons from the anion. So these electrostatic charges between these two oppositely charged particles forms the ionic bond between these two ions. So closer the nucleus to the electrons of the N ion, stronger is attraction between them and stronger is the ionic bonding. So if you have a larger cation and the same size of N ion, now this nucleus here in the cation is further away from the electrons from the N ion compared to the smaller cation in the example on the left. So the attraction of nucleus to the electrons of the N ion is also weaker. So these two examples, the one on the right hand side, the ionic bonding is weaker. So weaker ionic bond will release less energy compared to the formation of stronger ionic bond. So the lattice energy for the compound on the right hand side is less exothermic. For the one on the left hand side is more exothermic. We will now look at the second factor affecting the lattice energies, which is the charge on ions. Lattice energies becomes more exothermic with ions of greater charge. So higher the charge, more exothermic is the lattice energy. We have two examples here, lithium fluoride and magnesium oxide. Lithium fluoride has lithium cation with positive 1 charge and fluoride ion with negative 1 charge. Magnesium oxide has a cation of positive 2 charge, higher magnitude than lithium, and oxide ion, negative 2 charge. Again, the N ion has a higher charge than the fluoride ion in lithium fluoride. Lithium and magnesium ions have similar sizes. Fluoride and oxide ions also have similar sizes, but because of the higher charge on the cation and N ion in magnesium oxide, the cation and N ions will bond strongly to each other compared to the singly charged cation and N ion in lithium fluoride. Therefore, stronger ionic bond releases more energy. Lattice energy is more exothermic. Lower charge ions with similar size will release less energy because of the weaker ionic bond between the ions. Let's look at more examples in this table. So for the first 4 compounds, I have all halides of sodium fluoride to sodium iodide. If you look at the lattice energy becomes less exothermic from sodium fluoride to sodium iodide. Now this is caused by the size of the N ion. Fluoride ion will be the smallest one in group 17. Iodide ion is the largest. So the size of N ion is increasing, going down the group. Larger the size, less exothermic is the lattice energy. So now for the second group, I have group 1 chloride, sodium chloride and potassium chloride. So when the size of cation is changing, increases in this case, again, lattice energy becomes less exothermic. And another group, group 2 fluorides, the size of cation is increasing from magnesium to calcium. So lattice energy becomes less exothermic. Now I'm going to pick 2 more, sodium fluoride and magnesium fluoride, to look at their lattice energies. Sodium fluoride and magnesium fluoride, they have the same N ion, which is the fluoride ion. They have different cations. In sodium fluoride will be sodium ion, magnesium fluoride is magnesium ion. Magnesium ion is the one with higher charge. So stronger ionic bond is formed between magnesium and fluoride ions. Between sodium ion and fluoride ion, the ionic bond is weaker. So lattice energy of sodium fluoride is less exothermic compared to the lattice energy of magnesium fluoride. We will now look at what type of questions can be asked in the exam about lattice energy. The questions will usually ask you to compare the magnitude of lattice energy of 2 different ionic compounds. You are asked to compare the magnitude of lattice energy of magnesium oxide to that of sodium oxide. When you are asked to make comparison, write down their formulas. and identify the cations and anions in both the compounds. The type of ion, these two compounds have the same type of anion. So we are not going to compare common ion. So we'll compare the ions that are different in both compounds, which is in this case the cations, magnesium ion and sodium ion. So the two factors affecting the lattice energy, the size of ion and the charge of ion. So these two compounds, they have different sizes. Magnesium ion is smaller. The charge, magnesium ion has larger charge than sodium ion. So we need to talk about these two factors in your answer. We will answer this question part by part. The first part will be how would you expect the magnitude of lattice energy of magnesium oxide to compare with that of sodium oxide. So the lattice energy of magnesium oxide will be larger than that of sodium oxide. Because we are only talking about the magnitude, stronger ionic bond between magnesium ion and oxide anion. So energy that is released will be more, so lattice energy will be larger. Now we explain the reasoning by using these two factors. The size of magnesium ion is smaller than sodium ion. What about the charge? Magnesium 2 ion has larger charge than sodium ion. Don't forget the last line must always include this last line. Stronger ionic bond between Mg2 plus and O2 negative. So to answer question like this, if you are asked to compare the magnitude, then talk about the two factors and your answer with stronger ionic bond between which two ions. I included the mark scheme also so that you can compare your answer with. Let's look at another question. In this question, you are supposed to compare the lattice energies of calcium fluoride and calcium sulfide with that of calcium chloride. You can pause this video to try to write down your answers. Then when you come back, I'll show you my answers and also my explanation. To solve this question, again, I will identify the cations and anions in the compound. So we can see that all three compounds, they have the same cation, which is calcium 2. So we are not going to compare cations. We will be comparing the anions in this question. Between calcium fluoride and calcium chloride, the size of fluoride ion is smaller than the size of chloride ion. So let's write down that one first. So that will be the first factor, the size of ion. And now we look at the charge. Now both of them have the same charge, -1. For that cannot be in our explanation because same charge will not explain why they have different magnitudes of lattice energies. Now let's look at the second one, calcium sulfide with calcium chloride. The two anions, they have similar sizes because both of them are in the same period. Across a period, size of anions are decreasing. Sulfide is on the left-hand side of chloride ion in the period table. So they have similar sizes. So in this case, we're going to talk about the charge on these two ions. Sulfide has a larger charge. So larger charge will contribute to stronger ionic bonding, therefore more exothermic lattice energy. So in this case, the explanation will be the sulfide ion has a larger charge compared to chloride ion. Now, after comparing the size and the charge of these anions, we can suggest how the lattice energy of calcium fluoride and calcium sulfide is different from that of calcium chloride. The size of fluoride ion is smaller than chloride ion, so the lattice energy of calcium fluoride will be more exothermic than lattice energy of calcium chloride. So we are supposed to compare in terms of magnitude only, so it will be larger. Second part, sulfide ion has larger charge compared to chloride ion. So again, lattice energy of calcium sulfide, its magnitude will be larger than the lattice energy of calcium chloride. You can look at the mark scheme to see how marks are allocated for your answers. Another question will be to compare the magnitude of lattice energy of barium sulfide to that of barium oxide. So first answer, it is greater or less than the lattice energy of barium oxide, and then explain. So you should again pause the video to write your answers and then come back and check your answer against mine. So same thing here. Let's identify the cations and anion in these two different ionic compounds. They have the same cation, so we are not going to compare the cations. We are only going to compare the anions in this question. One of them contains sulfide ion, the other one oxide ions. Both sulfide ions and oxide ion, they have the same charge, -2. So we should compare the size of these two anions. Oxygen and sulfur, they are both in the same group, group 16 in periodic table. Oxygen is in period 2 and sulfur in period 3. So sulfide ion has a larger size compared to oxide ion. So the ionic bond between barium ion and oxide ion will be stronger. So the magnitude of lattice energy of barium sulfide is less than that of barium oxide. We'll look at one last example on this type of question from a very recent paper, March 2024. Question says that the ionic radius of lead-2 ion is 0.120 nanometer compared to the 0.133 nanometer for potassium ion. We are given two compounds here, lead-2 iodide and potassium iodide. We will suggest how they are different and then explain our answer. Pause the video to try answering this question and then come back and check your answers. So let's identify the cations and anions in these two compounds, lead-2 and iodide, potassium ion and iodide ion. Ions are in common, so we are going to compare only the cations. That's the reason why the question is giving you the ionic radius of the cation but not the ionic radius of the anion, because we only have to compare the cations in this question. So first we look at the charge, then we look at the size, the two factors affecting the lattice energy. Lead-2 ion has a higher charge compared to potassium ion. And we will compare size. The size is given, so potassium ion is larger, lead-2 ion is smaller. So right now, the next explanation, lead-2 ion has a smaller size. Larger charge, smaller size, what does it tell us? Lattice energy of lead-2 iodide will be more exothermic than lattice energy of potassium iodide. So lattice energy of lead-2 iodide is more exothermic than lattice energy of potassium iodide. Now do not forget that you have to end your answer with one last line, which is stronger ionic bond between which two ions? In this case will be lead-2 ion and iodide ion.